This meeting is being recorded.
So I've shared my screen. Can you see my screen? So last week we discussed we started discussion with dielectric properties of solid, and we are able to go to the extent of discussing up to the point where when you have two local electric field, and from there on, there was a problem on dipole, which I said you people should look at and see if you can demystify the concept. So is there anybody in the room that tried to solve the problem? So I'm talking of this particular concept. I think we stopped here last week. Here. So I asked you to look at this and also see how you can derive this part. So once we have this part, others are very simple to simplify. Is there anybody that tried it? Victor, did you try that? CD card, did you try it?
No, sir.
No, did you try it? No, why? But I said you should try it now to see if you can use this diagram here to be able to justify what you have here. Okay, anyway, I think I can share my own solution with you. So, do you see the screen? Can you see the screen? Hello, can you see the screen?
Yes, I can.
Hello?
Yes, I can.
Okay, fine. So if you look at the picture in the course material, you have something like this. A negative charge Q and a positive charge Q separated by a distance D. So I label this point A and this point B, and the middle of this point as point O. So there's an angle theta between XO with respect to B. So you have along XB to be equal to R1 and along XA to equal to R2. So to demystify this, what you just need to do is you extend this point O, down a bit, like what I have here. If you extend it down up to this point, I call it point phi. Then you allow it to form a kind of a perpendicular to this. Then you have a right angle triangle. And since it's the half of the distance here, so this will be from A to B to be D over 2, and from O to B will be D over 2. Then you can actually use triangular laws. So I say, if you look at this now, from V to X now, that is SV, the length consists of VO, OT, and TX. This T is coming from this place. Just draw a line from here that will form a perpendicular to this line. So it is combination of these three things that give us SV. So that's it. If you look at from triangle AOV, that is AOV now. So you can say that cos theta, this angle now, cos is adjacent over hypotenuse. This is OV all over AO. You have this. So our OV, we don't know it, but we know our AO, which is hypotenuse, D over 2. By the time you perform the operation, it will be 2OV over D. So 2OV is now equals to this, you multiply cos, you give you D cos theta. If you do the same thing for this point, BTO or BOT, you have something like this as well. OT is the adjacent to the theta, and OB is the hypotenuse. So you see that at the end of the day, you have TOT to equals to this cos theta, though these two things are equal. So if you now come back to the picture now, that from X to B now, which is R1, we can say that R1 is equal to BS, which is approximately XT. Because if we look at this now, it's more or less like the distance from this place to this place is same thing as this, because it forms a kind of an isosceles triangle. So the two sides are equal. So if that assumption is taken into consideration, then we can say that OT now is equals to, since we know that from this place, from X to O, we have OT in between. So if you take this OT away from X to O, you get what R1 is. And that is what gives us this. XT is now equals to OS minus OT. So OS is R, then minus D cos theta over 2, which is this one. Where is this? OT. This is our OT. So if we perform the operation, the denominator is 2, the common factor between them is 2. Then you have something like this. If we do the same thing for R2, in R2, you see that the distance from here to here is R2, which is AX. And it's more or less like AVX, this distance. So if that holds, so we can now say that SB is equals to OX plus OV. So OX is R, then plus D cos this, and this gives us this. So if you now find the reciprocal of 1 over R1 and 1 over R2, you have this. R2 will give us this. And you know that when you are computing the potential, if you look at this formula, this formula is trying to tell us that we need 1 over R1 minus 1 over R2 to be able to determine this potential. So if you take that into consideration, then looking at this, you have 1 over R1 minus this. That will give you this. We know 1 over R1 to be this, 1 over R2 to be this. So by the time you put them together, you have this expression. Something will cancel out. If you take your pen and pencil and work it out, you see it. Then you have 4D cos theta over 4R squared minus D squared cos square theta. Now, if you take consideration that if R is far greater than D, the whole of this goes to 0. Then you now have 4D cos theta over 4R squared. So 4 will cancel 4, then you have D cos theta over R squared. So this one now, if you come back to this formula here, we have this expression. From these two things now, we have this expression, and which we just derived. By the time you put it together, then you now have the dipole moment P is the vector along the axis of the dipole pointing in the direction of minus Q plus to plus Q and having magnitude of QD. So since we have this now derived, by the time you put it in the formula, because it's replacing what we have just derived, is replacing the whole of this now. You are replacing the whole of this. So with D cos theta over R squared. So now since we have P, Q, and that's dq, that Q is now the dipole moment. So we now have this. This multiply this, D and Q will be P, which is what you have here. Then cos theta over R, this one is a constant, then R squared, this. But if you look at this expression now, if you take the gradient, the grad of 1 over R, it will give you this. What we are trying to do here is that we take derivative of this now, 1 over R, keeping 1 over R constant. By the time you perform the operation, you have this. So if you substitute it inside this expression now, you have picked 1 over R here, you are left with 1 R. So if 1 over R gives us this, then you take this to multiply this now. You now have P R dot R bar over R cube. You have this expression now. So from this concept now, we can rewrite it as this is equals to this. We are still referring to this expression. So this gives us, so the whole of this now, the whole of this, if you take this out and you put this as a constant, you now have minus P, that is dipole moment, dot, this is now the divergence of grad of phi. So phi is the potential of a unit charge. So the field of an electric dipole may also be expressed in the following way. So we know that if you know the potential, you can also determine the electric dipole, so which is going to be in this form. So by the time you perform analysis on this now, just a kind of a vector notation, you are going to have this expression. And the same thing goes to this, and eventually we have what is called the electric dipole. Any question on that? Any question? Okay. So now say considering a cubic crystal dielectric, that is what we have in figure 1.2. This is our figure 1.2. This one now. If you look at this now, we have two types of dielectrics in this place. This is in a sphere and this is in a cylindrical coordinate, in a cylindrical rod. So when you have E naught, which is applied field now, you have this negative charge and positive charge. So dP here is the polarization of electric field. And the same thing is in a rod, you have something like this. So let's see what that discussion trying to say, that assuming an electric field of magnitude E naught is applied parallel to one of the axes of the crystals. So the field will push the positive charge nucleus of the atom of the dielectric slightly in the direction of the field and negative charge electron in the opposite direction. So what they're trying to say is that if you apply an electric field parallel to the axis of the crystal, the field will push away the positive charge nucleus of the atom. So because they are more or less like the same, we say like charges repel while unlike charges attract. So because they are like charges, they will repel each other. So it will push it away. So, and dielectric is in the direction of field and negative charge electron in the opposite direction. So the negative will also come in the opposite direction to look for an electron to attract to. So we say that the atom is polarized. So under the influence of applied external field, and the charge are called polarization charge. So what we're trying to say is that if you apply an electric field into a crystals, something will happen. What happens is that you have what we call polarization. Polarization, that is, you have splitting of the charges. So the positive charge will go in one direction and the negative charge also go in one direction. So this thing is called polarization of charge. That is, in the presence of external field, the charge are what? Polarized in different directions. So the polarization P, now the definition of polarization P is the dipole moment P per unit volume. So if somebody has to define what is polarization, it is just the dipole moment per unit volume, average over the volume of a cell. That is, when you find the dipole moment per unit volume, then you divide it over the volume, over the average of the volume of the cell. So the total dipole moment is defined as this. So if you have different polarization field within a particular crystal, so the combination of all of them will give you the total dipole moment, which is defined by P bar is equal to summation of Qn and Rn. Qa is the charge and R is the distance. So now we say let us imagine that a small sphere is cut out of the specimen around the reference point. Then E1 is the field of the polarization charges on the inside of the cavity left by the sphere, and E2 is the field of the atoms within the cavity. So the polarization charges on the outer surface of the specimen produce the polarization field E3. So the depolarization field is opposite to P, that is the polarization. That is, the electric field E is called depolarization field because within the body it tends to opposite the applied field E naught as in figure 2. So what I'm trying to say is that if you look at figure 2 here now, if you look at this now, they cut this part and this is applied field, is going like this. So polarization is also moving in the opposite direction of this field. So they are not moving in the same direction, but they are moving in what? Opposite direction. And the charges are separated. You have negative charge one side and positive charge in another side. So we say that the dielectric acquires a polarization due to applied electric field E naught. So the concept is that if you have a crystal and you have dielectric of the crystal, once you introduce an external applied electric field, the dielectric of the material will surely absorb what you call polarization. This polarization is the consequence of redistribution of charge inside the dielectric, meaning that in the presence of applied electric field, polarization will take effect, and when polarization takes effect, it actually affected the charge distribution within the dielectric. So the local electric field, ELOC, at any point of the dielectric may be written as this. So now you have the initial one, which is the applied one, the one created within The one also created as a result of the cutting, and this one created as a result of redistribution. So the combination of all of them will give us the total effect at one atom of the dipole moment of all the other atoms in the system. So we have something like this, which is more or less like the formula we derive here. This 1.15b, this formula. So this gives us this. And in an SI unit, you have something of this nature. So you don't need to cram a lot of things. Just understand what this concept is all about, like I was explaining. So this is a kind of polarization in spherical dielectric and also in rod. So somebody can ask you to discuss how polarization take effect in a spherical material and also in a thin rod. It's more or less like what we have just discussed. So now, if you look at Lorentz, show that feed E1, which is feed E1 due to the polarization charges on the surface, form a continuous distribution. What this is trying to tell us that when you have feed E1 due to polarization on the charge of surface, this is continuous in nature. That is based on Lorentz concept. So the density of the surface charge is equal to P cos theta, like we derive when we are looking at triangle, where theta is the polar angle along the direction of polarization. So if you look at this picture now, this is a sphere now. Then you have a distance from here to this place. Then this is A. But if you consider redistribution of charge in this place now, then you use Lorentz transformation using this equation. You have something of this nature, which is 4 pi P bar over 3. This is more or less like the volume in a sphere. So the feed E2 due to the dipoles within the spherical cavity is the only term that depends on the crystal structure. It can be shown that for a reference site which could be surrounding in a sphere, that E2 is equal to 0 if all the atoms may be replaced by a point dipole parallel to each other. Once you have a parallel point dipole to each other, E2 is always 0. That is the concept you should take into consideration. So for specimen in the shape of ellipsoid, so now for specimens in the shape of ellipsoid oriented with one of the principal axes parallel to the applied field, it can be shown that the depolarization field will be parallel to the applied field, and electric field will be this, N polarization over epsilon naught. So the constant N is known as depolarization factor. If PS, PY, PZ are the component of the polarization, that is, if you consider the polarization along X, Y, and Z, that is in three coordinates, that is in the three cardinal coordinates. So P refers to the principal axis of an ellipsoid. Then the component of depolarization field are written as this. So you now have it for each of the direction. NXPS over epsilon naught. This is for Y minus this. This is for Z, like this. So now, assignment for you is to explain what is polarization and depolarization field, and what are dielectric, and define dipole moment. What you do is that you do this work, then you send to me by email. Are you with me? Can you hear me? Hello? Okay. So this is an exercise for you. You solve this problem, explain what is polarization based on what we have just discussed. What is polarization and what is depolarization field? Also, what are dielectric? I've discussed this with you last week. We just discussed polarization and depolarization now. Then I've defined what dipole moment is. So look at the note, extract the information about these three things, then send the answer to me by email. Is that taken?
My network has been poor. I'm just coming online. Good evening, doctor.
Okay, sorry. So if you have any question, you can ask before we move to the next thing, which is dielectric constant and polarizability.
I don't know if you have given us the answers to the thing you gave us the other time about the proof of dipole. Of course, network distorted my decision.
Yes, I've given an answer to that. I can quickly show you. This is the proof. So this is the proof. So I've discussed that already. But by the time, if I upload the recorded version of this lecture, you can see how the discussion looks like. But I can as well send you this document.
Okay, if I'll be very glad, sir. If I can have it.
Yes, I will send you the document. I will upload the document on the course webpage, then you can download it there.
Okay, sir.
Is that working? Okay.
Yes, sir.
Okay. So now let's move to the next thing, which is dielectric constant and polarizability. So please, can you mute yourself because of echo? I think Victor and Godwin, please mute your mic because of echo. So now let's consider the dielectric behavior of molecules, which have a permanent dipole moment. What we're trying to say here is that in molecule, there is tendency for molecule to have a permanent dipole moment. So let's see how the dielectric behave. So the dielectric constant epsilon has been defined for an isotropic or cubic medium relative to vacuum as. So in a vacuum or isotropic, that when you say something is isotropic, is directional dependent. If it is anisotropic, is directional independent. Please, Godwin, can you please mute your mic? Okay, thanks. So now we have epsilon to be equal to D over E, which is equal to 1 plus P all over epsilon E, and is equal to 1 plus epsilon. This D here is displacement. So Y psi is the electric susceptibility. So the susceptibility is related to the dielectric constant by this. So this is P over epsilon E, which is equal to E minus 1. This is the relationship between dielectric constant and susceptibility. So if the field is not too large, so please pay attention to this now, because this is the physical interpretation of this expression. Say if the field is not too large, the strength of the induced dipole moment in an atom I is proportional to the local electric field acting on the dielectric. That if you have a very low field, you have a kind of a direct relationship between the dipole moment and the local electric field. So which is given with this equation, Pi proportional to the local electric field. And Pi is equal to alpha I, then E LOC, which is the local electric field. So where alpha I is the polarizability and Pi dipole moment of an atom I. So meaning that at each point where you have an atom, you have dipole moment per atom and also polarizability per atom. If the atom is 10, you have for each of them. So polarizability has the SI unit of this, but it's more often expressed as polarizability volume with unit of centimeter cube or Armstrong cube, which is equal to 10 to the power of 24 centimeter cube. So polarization of a crystal may be expressed approximately as the product of the polarizability of the atoms times the local electric field. So now, if you are defining what polarization is just the product of two quantities. And what are those quantities? The polarizability of the atoms times the local electric field. That is, each of the atoms has its own polarizability. Then multiplied by the local electric field per atom. So you have what is called polarization. So this is what we have here. P is equal to the summation of I, Ni, Pi, meaning that for each of the atom, each of them has its own polarization. By the time you add them together, you give what? The total polarization of a crystal in an atom, where Ni is the number per unit volume of atom I. Now, if we can combine this formula to also determine electric susceptibility, which cannot be defined as this. We say that susceptibility is equal to P over E. We defined that here some minutes ago, which is this. So in this case now, there is dielectric.